Okay, so we learned geostrophy. I'm sure you mastered it by now. Make sure you understand it correctly because you'll be able to apply it in many situations. So let's now look at the concept being applied to ocean circulation. We introduced it obviously because it's important for ocean circulation. So we are now going to combine our Ekman currents, Ekman transport, and see how it can lead to geostrophic currents, right? So you had northeasterly trades just stay in the northern hemisphere, let's say in the North Atlantic. You have northeast trades dragging the ocean from off the coast of Africa towards the coast of South America in the deep tropics. So the Coriolis is going to push it to the north, so water that's moving west is going to be transporting water to the north, and you have mid-latitude westerlies pulling water from the US or North American coast towards African and European coasts, right? That eastward flowing current is also going to be transporting water southward because Coriolis is going to push it to the right, to the south. But Coriolis effect is higher at higher latitude. So more water is being pushed to the south in the mid-latitudes by the westerly driven eastward current, westerly wind driven eastward currents, than the easterly driven, northeasterly trade wind driven westward current. So essentially you have more water coming south. So there is a southward mass transport meeting the smaller northward mass transport. So you're going to have water pile up in the middle. Okay, so if you go from the equator to the middle of the subtropical gyre, you are going to have an increase in sea level of almost 2 meters. 2 meters. So 2 meter high pile of water, which means gravity is going to create flow down the hill, right? As water starts to move down the hill, you have Coriolis acting on it. So you can see the figure here. You have geostrophic flow happening when the flow is moving from the dome in the middle. So Coriolis is acting, so we are looking at the south to north. Coriolis is going west to east, so centrifugal force is pushing you to the east, as is shown here as the rotation of Earth, and the water that's piled up in the middle is flowing, creating flow of water in every direction down the hill. Obviously we are looking at one side. The water that's flowing down is going to be pushed to the right, so you have flow happening essentially around the dome. Okay, imagine that for yourself. Make sure you understand it. Dome of water, water flowing down, tilted to the right by Coriolis, so now going parallel to the dome. So you have these flow lines around the dome, and Coriolis is obviously pushing to the right, so it's to the right in this blue arrow. Gravity is pulling it down, so it's towards the bottom of the hill mound of water, and the two are going to balance and create this subtropical gyre. So you have convergence of water in the middle, creating a pile. The convergence is happening because Coriolis is pushing more water to the south and less water to the north. So it's not only creating a convergence, but it's creating it more towards the south, and so on. Okay, so it's a very simple figure, but make sure you stare at it and you understand it, because we said geostrophic currents are important when there is no friction. Here water is just moving down the hill by gravity, and Coriolis is balancing it to create geostrophic flow. But the dome itself, the pile of water itself, is created by winds, and for winds to drag the ocean, friction is important. Okay, so Ekman currents and Ekman transport are creating a dome, and the geostrophic flow that's happening because of the gravitational gradient by the pile of water is geostrophic because the friction there is negligible. Okay, so again, very simple concepts, but what we are doing is now we are adding more and more details. So many pieces of information, each piece of information is very